So we've done calculations for pH, but we need to make really certain that we understand our terms strong acid and strong base. So let's start out with strong acids. Strong here means strong electrolyte, meaning if you put a strong acid in water, it is going to ionize 100% into its H plus and its Cl minus. Now, we can write it either with a reaction with water, or we could write it as HCl is going to ionize 100% into H plus plus Cl minus. Note this gives us one arrow. One arrow here is always going to mean 100%, and we're going to use it for our strong acids. In a weak acid, it means a weak electrolyte. And a weak electrolyte means that it's only going to partially ionize. If it's going to partially ionize, inherently you're going to get an equilibrium. So if we have any weak acid, it means we're going to have an equilibrium problem. Well, if we have an equilibrium problem, it tells us that we need to look up the K, we need to do an ice chart, and we need to solve for F's. So strong acid, 100% ionization, meaning if I start out with 0.1 molar of HCl, at the end I'm actually going to have 0 HCl because it's going to react 100%, and I'm going to end up with 0.1 molar H plus and 0.1 molar Cl minus. Strong 100%. Make sure you have committed to memory the strong acids: perchloric, chloric, hydroiodic, hydrobromic, hydrochloric, nitric, and sulfuric, first hydrogen only. You need to have those committed to memory. While we're at it, let's make sure we got the strong bases as well. Now, strong bases don't ionize, they dissociate. So we're going to take and we're going to put them in water. Our strong bases are going to be our inorganic group 1 and group 2 hydroxides, and they're going to break apart into their ions, into the cation and the hydroxide. If it's going to be like a sodium hydroxide and it's a group 1, you'll make 1 hydroxide. If it's a group 2 hydroxide like barium hydroxide, you're going to make 2 hydroxides. Make sure you memorize those as well, and those are the group 1 hydroxides, as well as calcium, strontium, and barium hydroxide. So have those as well committed to memory. So we're going to start out here with a solution of 2 times 10 to the minus 3 molar of nitric acid. We know nitric acid is a strong acid. We've committed those to memory. We know that that means that when we put it in water, it's going to ionize 100% into H plus and NO3 minus. So if we start out with 2 times 10 to the minus 3 molar HNO3, it is going to react 100% to make H plus and NO3 minus. Again, what does that mean? It means that when the reaction is finished, we're actually going to have 0 HNO3, and we're going to have 2 times 10 to the minus 3 molar of each of the nitric acid, or excuse me, the H plus and the NO3 minus. We want the pH of this solution. We know that pH, by definition, is the minus base 10 log of the concentration of H plus, which is 2 times 10 to the minus 3. And if you plug that straight into your calculator, you're going to get a pH of 2.70. Okay, so what if instead we do the pH of 1.8 times 10 to the minus 2 molar of barium hydroxide? So what's going to happen? If we start out with barium hydroxide, and we put barium hydroxide in water, and by the way, you can do this for nitric acid as well, and look at the pieces it dissociates into. And we can do kind of like an ice. It's not equilibrium at the end. We're just going to call this a final rather than an E. If we start out at 0.018, just putting that in standard notation, and 0 and 0, this is going to go down by 0.018, such that we have 0 left. The barium is going to go up by 0.018, but the hydroxide, because there's 2, is going to go up twice that, and it's going to go up by 0.036, such that at the end here we have 0.018 and 0.036 molar. In order to get the pH, we're going to get the POH first. POH is going to be minus base 10 log of 0.036. That will work out to be a pOH of 1.44. We know that pH plus pOH is 14. So if we take 1.44 and we subtract it from 14, we're going to get pH is equal to 12.56. All right, strong. We have to immediately identify whether or not we have a strong acid or a strong base, because with a strong, it's going to react 100%, one arrow. With the weak, we're going to get an equilibrium. We're going to have to do an ice chart and an X. So what do we mean? So if we have a nice weak acid, so let's imagine here that what we have is HF. HF is not on the list of strong acids that we've memorized, so we know it's weak. We know it's going to dissociate in water partially to make H plus F minus. Now, the amount of which it will dissociate depends on the concentration, but what we mean here by weak is that if we put it in water, only a small amount is actually going to break into pieces. If we have a weak acid or a weak base, we're inherently going to have an equilibrium problem, because weak means weak electrolyte and weak means two arrows, because reaction is going to go in both directions. In fact, it's going to favor the reactant side because it's weak, which means a small k. And so when we do this, we can write this two ways. One, we can take our acid and react with water to make hydronium plus the conjugate base, or we can leave the water off and go straight into acid, and we're going to use a generic form of our acid. So if we have any generic Bronsted acid, we're going to take and write it as an HA. When it reacts, it's going to donate the H plus to water, and it's going to leave us with hydronium and A minus. So if we have a generic Bronsted acid, it's going to be a formula of HA, and its conjugate base is going to be A minus. If we look at the shorthand for the reaction, we're going to get HA dissociates into H plus and A minus, such that Ka is equal to the products over the reactants. We can leave the water off, of course, because it's a pure liquid anyways. And Ka here is just the equilibrium constant, and we're going to call it the acid ionization constant. In fact, we're just going to call it Ka. Now, as the value of Ka goes up, the strength of this weak acid also will go up. For example, if we take HF and we put it in some water, we know this is a weak acid, so we're going to get two arrows. It's going to make hydronium and fluoride. If we do this shorthand, we're going to have HF reacts with water to make H3O plus and F minus. Equally shorthanded, we could have HF reacts to make H plus F minus, and the K for this, which we're going to call Ka, the acid ionization constant, is going to either equal hydronium times fluoride over HF, or H plus multiplied by F minus over HF. You're going to look up the Kas in the back of your textbook and use them for the problems that we're going to be doing. So if we have a weak acid, the first thing we're going to do is write the equation. So remember back in chapter 13 when we were talking about this, and I always said the first thing to do is write your balanced equation. Well, the balanced equation with any weak acid or base problem is going to be a simple hydrolysis. So you're going to take your acid here and you're going to react it with water. Once you take your acid and you react it with water and you set it up so it's weak, which means that you have two arrows. Well, as soon as you have two arrows, you need an ice. If you need an ice table, you're going to solve for X, and you're going to look up your Ka, and you're going to solve something. Now, we're going to try to do it by approximation. If we can't, we're going to have to solve it exactly, which means we're going to have to use the quadratic. We're either going to solve for concentrations or the pH of the solution. I'm going to define a term quickly, and that is percent ionization. Percent ionization is going to be how much of the acid we make at equilibrium, which is this concentration of H plus or hydronium, over the initial concentration of whatever the acid is multiplied by 100. So if we have a monoprotic acid, which is really all we tend to do it with, percent ionization is H plus over HA, initial, times 100. But note, H plus is also equal to our X value, how much we've been solving for in our ice table. So our percent ionization, how much of it actually ionizes, is going to be X over the concentration of your acid, initial, times 100. Why do we care? Because if our percent ionization is going to be less than or equal to 5%, we're going to use our approximation. So let's calculate the concentration of HF in a solution and think about that. So what is the pH of a 0.5 molar solution of hydrofluoric acid at 25 degrees Celsius? Well, 25 degrees Celsius just tells us that we're going to be able to go to the back of our book, go to our Ka charts, and we're going to find that our Ka for HF is given to be 3.5 times 10 to the minus 4. And we know that our Ka, looking at our nice balanced reaction, or hydrolysis reaction, and again, if we want to do a complete hydrolysis, we could take our HF, react it with water, give us our two arrows, make our hydronium plus an F minus. It doesn't change what our form of the equilibrium constant is because we're going to take the water out anyways. So we're going to know here that our Ka is going to equal the concentration of H plus multiplied by F minus over HF, which means we have to take and dig through our ice chart to figure out what our values are here at equilibrium. So what do we know? We know we start out with 0.5 molar. We're going to, and since we have no other values of fluoride or H plus, we're going to set those values at the beginning equal to 0. We know that the concentration of HF has to go down. This reaction is 1 to 1 to 1. So our HF is going to go down by X. Our fluoride and our H plus are going to go up by X, such that at equilibrium, for HF, we have 0.5 minus X. Fluoride is X, and H plus is X as well. We have our Ka, 3.5 times 10 to the minus 4, is going to equal X times X over 0.5 minus X. So what was our assumption? Our assumption here is that if our K is small, if K is small, and by the way, if it's less than about 10,000, which this one is, this is small. If K is small, then we're going to say that 0.5 minus X is about equal to 0.5. That the reaction lies so far on the side of the reactants over here that any change is negligible. So we're going to set that X value right there equal to 0. This one here, we're going to set equal to 0. Now, this dramatically simplifies our math because now we have 3.5 times 10 to the minus 4 is going to equal X squared over 0.5. And when we solve for X, we are going to get X here is equal to 0.013. And when we solve for X, we've got to make sure what we're looking at. X here is the concentration of the H plus. So we need to write that down so that we can look at our next step. And our next step is pH. Well, pH is the minus base 10 log of the concentration of H plus, which is equal to minus base 10 log of 0.013. And the pH of this solution is going to equal a value here of 1.88. So, is this a good assumption? Can I assume that 0.5 minus x is about equal to 0.5? And remember when we said that if our percent ionization is less than 5, our approximation is good. Well, if we take our x value, 0.013, divide it by the initial, so our x over the initial of the acid, times 100. We do the math here, we're going to get 2.6%. That is less than 5, which tells us this approximation is valid. Now, what if we changed our concentration? Well, if we did the same thing, but instead of starting with a value of 0.5 molar HF, we have 0.05, and we plug it through and do the same math. If we do that, you would find that our X value is 0.042, and when we do our percent ionization, where that is equal to X over the concentration of the acid, initial, that's going to work out to 8.4%. In this case, that is greater than 5%, and our approximation is not okay. Closer the value of the concentration and the Ka get, the less valid our approximation is. In this case, we would have to use the quadratic. So let's do another one. What is the pH of a 0.12 molar solution of acetic acid? Well, first of all, you don't even have to know what the formula of acetic acid is. We know, one, that it's weak. How do we know it's weak? Because it's not on the list of strong acids we memorized. Anytime you have a weak acid, you can just call it HA and you can run from there. If you don't like that and you need to visualize it, acetic acid is an organic acid and it looks like this. So if we do this, we know it's weak. If it's weak, we have an ice chart. So we're going to start out with CH3COOH. We can take and we can react it with water, or we can leave the water off. It makes absolutely no difference because we're going to ignore the water anyways. Making hydronium plus the conjugate base. And we're going to find that Ka, which you're going to look up in the back of the book. And when you look it up, or you can Google it, you're going to get 1.8 times 10 to the minus 5 is equal to the concentration here of hydronium times acetate divided by the concentration of acetic acid. And we know we have to get these values here on the E portion of our ice chart. So we're going to set ourselves up an ice chart. We're going to start out with 0.12. We're going to ignore the water because water is a liquid. We're going to assume 0 here, or we're going to ignore the contribution from the water. Water's got a very, very small amount of H+, so we get to ignore it. This is going to go down by X. So we're going to have 0.12 minus X. This is going to go up by X and X and X. So we're going to have 1.8 times 10 to the minus 5 is equal to X times X over 0.12 minus X. Now note here, K is small. K is small. The first thing we're going to do is set this value of X on the bottom here equal to 0. And we're going to assume that 1.12 minus X is about equal to 0.12. Again, why? Because K is small. If we continue and we do the math, so we take our 1.8 times 10 to the minus 5, multiply by 0.12, realize that's equal to X squared, and then we're going to square root both sides. You're going to get that X here is equal to 0.0015. X corresponds to the concentration of hydronium. So our pH of this solution is going to be minus base 10 log of 0.0015, and the pH here is going to equal 2.82. Now we can look at these problems in a few different ways. Here we have a weak acid. Weak acid, we don't know what it is. It's just a weak acid, so we're going to call it HA. We're given the original concentration. So this is the concentration of HA initially. How do you know? Because it's a weak acid when the original acid is put into water. And the pH, which means here at equilibrium, is equal to 3.45. So what do we need? Well, if we have some weak acid, HA, we know it's either going to dissociate into H plus A minus, or we can put the water in there if we like. And we know that Ka is going to equal concentration of H plus multiplied by A minus over HA, and that these are the values at equilibrium. And we think about this, we do our ice, and we know we're going to start out with 0.25 of this, and these are 0. Now we have one more piece of information, and that is the pH. This is the concentration, or the measure of the concentration of the H plus at equilibrium. We know that the pH here is 3.45, and we know that this 3.45 is equal to the minus base 10 log of the H plus. Well, we know we can get rid of the H plus by taking 10 to both sides. So if we do that, we're going to get that 10 to the minus pH is equal to the concentration of H plus, or 10 to the minus 3.45 here at equilibrium is equal to the concentration of the H plus. Well, that's just a number, and we can plug that into our calculator, and when we do that, we're going to get 0.00035 molar. Well, what does that tell us? It tells us that this value is 0.00035. Well, if this one went up by 0.00035, then the A minus went up by 0.00035. Our change here, our HA, went down by that value. And at equilibrium, we have 0.25 minus 0.00035. Well, we know we can plug this straight into our equation for K, for our acid ionization constant. And when we do this, we're going to get our Ka is going to equal 0.00035. That's multiplied twice, so we can square it, divided by 0.25 minus 0.00035. When you do your math, if you'd like, you can ignore this part compared to the 0.25, or you can plug it in and use it, whatever makes you happy. It's going to be small with respect to 0.25. And when we finish the math, we're going to get that Ka is 4.9 times 10 to the minus 7. All right, now we have a weak acid, and instead of being given its pH, we're given the percent ionization. So we have to make sure we understand what that means. 6.5% ionization means that 6.5% is equal to our X value over the concentration of the acid initially multiplied by 100. Remembering here that X is equal to the concentration of H plus and the concentration of A minus. So here we have 6.5% is equal to our concentration of H plus divided by our initial concentration of the acid, which is 0.1, multiplied by 100, and this allows us to solve for H plus, and that will give us that H plus is equal to 0.0065 molar. Well, H plus is also equal to A minus, so that's equal to the concentration of A minus, and so we know both of those. Now HA, well, HA is going to equal what we started with minus how much reacted. So HA is going to equal a value of 0.1 minus 0.0065. And so our HA here is going to equal, it's going to equal 0.0935 molar. And if we want to find our Ka value, well, our Ka is going to equal the concentration of H plus multiplied by A minus over HA, which is going to equal 0.0065 times 0.0065 divided by 0.0935, and we're going to get a Ka value for this particular acid of 4.5 times 10 to the minus 4. Which leaves us now with about as messy as it's going to come, because we have 0.1 molar chlorous acid and our Ka is 1.1 times 10 to the minus 2. We could equally write that in decimal form and have it equal 0.011 for our value for Ka. Please note this is not small. And because this is not small, we can't do the approximation, so we are stuck with the quadratic. So what do we know? First of all, we're going to write the reaction. HClO2, it's going to dissociate or ionize into H plus ClO2 minus. If we plug this into our ice chart, here we're going to get 0.1 zeros. This is going to be minus X, and plus X, such that we have 0.1 minus X for equilibrium amount of HClO2 and X and X for the ClO2 minus. plugging this into our Ka, because we know our Ka is going to equal the concentration of our H plus multiplied by the concentration of the conjugate base, ClO2 minus, divided by HClO2. And that's going to be 0.011 is equal to X times X over 0.01 minus X, excuse me, that's 0.10 minus X, this value right here. And we're going to have to do the math. If we write this out, 0.011 multiplied by 0.1 minus X is equal to X squared, and combine like terms, we're going to get that X squared plus 0.011 X minus 0.0011 is equal to 0. We're going to have to use our quadratic, and when we do, we're going to get two roots. We're going to get that X is equal to 0.028 and X is equal to minus 0.039. Well, we can't have a negative value, otherwise we'll have miracles. So our X is this. We're trying to find the pH of the solution. We realize that X is equal to the concentration of H plus. So the pH of the solution is minus base 10 log of 0.028. And that's going to give us a pH of this solution of 1.55.